we're going to work our way into the 90s today. And then on Friday, I'll talk about like what we currently use for SpinEcho. So SpinEcho, remember, that's where you correct the inhomogeneities that come from static field offsets, and you get a T2. You can get like an accurate to get rid of the star part of T2. But you can use it for other stuff too, but that's one of the main uses for it. In particular, because a lot of times you do a T2 image to see like if there's a tumor or something, or some swelling or something growing. So before I do that, I'm going to talk about this the frequency encoding direction doesn't wrap. So why is that? Is that possible? So if you actually, if you run a scanner, if the scanner technician will know that there's no wraparound in the frequency encode direction, but there is in the phase encode direction, or the second phase encode direction. And so why doesn't frequency encoding wrap? Because Marty said that frequency encoding is the same as phase encoding, so shouldn't it wrap? Yes, it actually should. So why doesn't it wrap? So any scanner person knows, wrap doesn't occur in frequency encode direction. So why is that? So it's only only in phase encode directions, possibly more than one. So why is that? Does that actually sort of make any sense? Because as we see from the Fourier transform, it's the Fourier transform in the phase encode direction isn't any different than the Fourier transform in the frequency encode direction. So why is that? So it's because there's two things that you can do in the frequency encode direction that you can't do in the phase encode direction. And so one thing you can do is you can just sample in the frequency encode direction, just sampled 2 times faster in freak. It's no cost to do that, because you're doing a readout. So so here's, let's just draw just the phase encode and the frequency. So here's the phase encode part, which we do after the RF pulse, but before we start recording data. And then here's the frequency encode part, where so this is this is phase and freak. So we could basically we can just, without losing any time, we could sample at that rate, or we could just sample it at twice the rate, phase oversampling. And so that doesn't kill any time doing that. And so we know what that will do. That will just sort of expand the field of view. Now that doesn't stop the wraparound, but it sort of like moves it further out. But there's another tricky way that you can stop the wraparound. And remember, I said you shouldn't think of MRI as the way MRI works as put a gradient on, change the precession frequency, and then use the Fourier transform to undo the precession frequency, essentially map frequency to space. That's one way of sort of thinking about it, but it's a kind of a garden path that gets you confused, and it sort of covers up the fact that phase and frequency encoding are the same thing. But if we go back to that viewpoint, when we put a gradient on, say we put a gradient on, from front to back. So here's our gradient. So this is, our gradient. then basically that's going to be, proportional to the frequency, precession frequency. And so one thing we can do, so that means that, at this point, the precession frequency is going to be higher, going to be lower over here. So one thing we can do is we can just take the signal that we get out, which has all these different frequencies in it, which I said, don't think of it that way, but it does. That's what's causing the phase wraps to occur. The fact that, these guys are ahead and spins at this end of the gradient are ahead and spins at this end of the gradient are behind. That's what's actually causing those little stripes of spin phase to occur. But there are different frequencies, and so what we can do is we can just filter them out. So we can just basically do like a bandpass filter. That's what would be called a bandpass filter. So basically, this is, bandpass, meaning like only let frequencies that are from here to here through. So if we do a bandpass filter, then we can get rid of the replicas because that's if you work it through, you can see that's the way to sort of like stamp out the wraparound. So wraparound does occur in the frequency encode direction. It's not magically different than the phase encode direction. It's just that we've got several ways of fiddling with it, and you can't. So this is so the second way. So that was, the first way was just sort of expand the field, expand the wraparound. But you could, analog or digital, analog, filter out, signal at edge. So it turns out you can't do that. So what about, so why can't we do this thing to the phase encode direction in order to fix the phase encode direction? So the problem is, if you did this, can't do with phase because, 2 times acquisition time. So why is that? Because you just turn the phase encode gradient onto a particular setting and then record some data. If you were going to record more phase encode steps, it's just going to take more time. So if we doubled our sampling of the fineness of the different phase encoding steps, we would have to double the time of the scan. So that's not going to work. And this one, we can't do this one with phase because the gradient isn't on. Because phase encode gradient isn't on. Okay, not on during recording. So when we're doing this recording over here, the frequency encode gradient is on, but the phase encode we just did before, and so we can't do this hack. And so you just have to put up with the wraparound. And that's for most things it isn't a problem. Like if you're talking about going this direction across the head, well, there's black on either side of the head, so it's not a problem. It is a problem like with the head and the neck. So the neck can sort of wrap around back into the top of the head if you've got if your field of view is not as big as the thing that you're taking a picture of. If you're taking a picture in this direction in the sagittal plane, you've got a body on one side. So, okay, so the bottom line is there. The bottom line there is that wrap does occur in the frequency encode direction because what causes wrap is just the fact that we're doing discrete samples. That's the fundamental thing that causes wrap, is that we're not sampling sort of like all the spatial frequencies in between each sample, and that even though we're sampling high spatial frequencies, that will generate RAP. So RAP does occur in the frequency encode direction, but in practice we can get rid of it. And so then you would want to make the frequency encode direction the one if you had a problem with your field of view not being big enough for what you were taking an image of. Okay. So now let's actually move into the 90s. So what we're going to talk about are and these pulse sequences, which sort of got popular in the 90s, they're actually still used. It's not like they're not used. They're still used today. And they're generally called, fast spin echo. So there's a bunch of these stupid acronyms that are just words that you just have to learn if you want to sort of, read these papers. And so we'll start off with SpinEcho, which we can call, I'm old enough so that I actually sat in the scanner for some real slow spin echo. So slow spin echo, is generally just called SE for spin echo. And I'll write out the sequence for slow spin echo so you can sort of see. So slow spin echo is like the morally upstanding spin echo. It's sort of good spin echo. It doesn't have any sort of weird artifacts associated with it, but it takes a really long time. So to scan your whole brain might take like 45 minutes just for one scan. So you'd sit in there 45 minutes later, and obviously if you're taking 45 minutes, well, there could be a lot of movement that's occurring in that time, and so we need faster spin echo. So the second one I'll talk about is fast spin echo. And unfortunately, that has a number of different acronyms. So it's called, FSE. That's to me the most rational one, fast spin echo. But a lot of times it's called turbo spin echo. Turbo spin echo, and then sometimes it's called rare. I can't remember what that stands for. Those are all the same thing. So I'll talk about that one second. This one is still commonly used. So, and then on Friday I'll talk about a newer sequence which I call really fast spin echo. Fast spin echo, and this one on our scanner, this one's called space, and so that's what's more commonly used by research, research fMRI. So we'll go over these two today, and then this one on Friday. And the reason to do it is you might wonder, like, why do we have to hear about the 90s? Well, it's hard to understand the later ones until you see like what the what went before, and so that's the reason to sort of go over these older ones. So, and sometimes for research purposes, you actually might want to do this one because that one is kind of like the cleanest signal, even though it takes a really long time. A lot of times you might say, well, it takes too long, so I'll just do a couple slices. If you're looking for some particular contrast, and so you might even use this one. It's not completely out of the question. So, and then we'll sort of look at why is it slow. So the plan is to over here we'll look at where we are in k-space. So this is our k-space. So that's the ky direction, stripes, horizontal stripe direction, and this is the kx direction, which is the vertical stripe direction, and sort of the intermediate directions are like tilted stripe directions. So this is the way people typically think of it, but remember what, a particular point in this space corresponds to some distribution of spin phase stripes across the actual brain. So, and then over here we'll put up the actual pulse sequence and see how that relates to where we are in K-space. And so the first part here is the RF in, so what we've actually, what we're stimulating the brain with, and then we'll, in these diagrams, we'll generally put, the Z and the Y and the X gradients here. And then here's the RF, out, what comes out of the brain. Okay, so the first thing is we just do a 90-degree pulse. So there's our 90-degree pulse. And what we're going to diagram here is what would we need to do if we wanted to get a T2 weighted scan. So that's the goal of this one. And so, and this is a 2D sequence. So I'll add one more here. So this is a 3D fast spin echo. That's one way we can sort of get really fast. These guys can be done in 3D, but I'm just going to diagram a 2D sequence. So this is 2D slice based. So we're selecting a slice, not exciting the whole volume. So this is a 2D sequence. So we first do our RF pulse, and since it's a 2D sequence, we have to turn on the gradient to set the precession frequency of just a slice, and then we play out a frequency selective RF pulse that will just excite that slice. So that's the first part. So what's going on there? Well, what I said is you can sort of think of the RF pulse as starting at the middle of that stimulus, and so here's the FID coming out, which we're not recording, which is the transverse magnetization dying away, T2 star. So we can sort of think of it as coming out of the middle there, and then how does that sort of correspond to what's going on in K-space? Well, what's going on in K-space is, let's just take the idealization that we started a bunch of transverse magnetization that wasn't dephased at all at the center of that pulse. That would put us at the center of K-space, because there's no that's the zero of K-space. There's no stripes in the X or the Y direction, and also not in the Z direction. But then immediately what happens is we've got a gradient on. And so what's that going to do? That's going to cause basically the stripes to appear in the third dimension of K-space. So it's going to cause stripes to occur that are like striping like in this direction in K-space, actually sort of like coming out of K-space, which isn't even visible on this diagram because I just drew the X and Y part, but there's a Z part also. But then we quickly fix them. And so by the time, so you could sort of consider at time A, right in the middle of the pulse, we were at the center of K-space, and then we came out of the board in the Z direction, and then we fixed it. And so now we're fixed it. So we're back at A now. So now we're actually back in the middle of K-space. So then what we do is we wait a little while and do a 180 because we want a spin echo. So there's the 180 pulse. And what that does is, whatever magnetization you had here is kind of like in the transverse plane. You imagine you just sort of flip the whole thing over. 180 degrees, and then whoever was ahead is behind, and vice versa, and then the same amount of time after that. So here's that tau time. The same amount of time after that, we get an echo. So basically at this time down here, there should be an echo. I drew it. It's a little more, the echo is a little bit more scrunched up in time than I drew it here, but I drew it that way so we can sort of see things a little easier. Okay, so that's our echo. That's what we want to record, and that's the one that's, you know, falling off as. So the peak of that guy is, you know, e to the minus t over t2. So that got rid of the star part of t2. So there's a couple other things going on before we go back to k-space. So when we do the RF pulse here, we've got to do a slice select for this too, because we only want to, if we're just doing a slice and we want to do some other slices at some other time, we need to actually have the slice select gradient on, and this 180 pulse has to be a frequency specific RF pulse, so it will just excite spins in that little slab. But now if you ever look at any pulse sequences, you'll see there's always some ears on the pulse sequence like that. So one of the little ears on there. And these little ears are the crushers. So you always have those on there, and so why? So what is that? So the idea of a crusher pulse is, say our 180 wasn't exactly accurate because, you know, different parts of the head have slightly different B0s, B1s, not B0s, B1s. So when you turn on the RF, it penetrates into the head, but it's not completely uniform, and so some of the parts of the head are going to have a bigger or less flip angle than 180. And if it's bigger or less than 180, what's going to happen instead of just flipping it? So what we were hoping is, you know, we started off, you know, with that magnetization, and then we flipped it. We were aiming for that, but what if instead of that we got, you know, something that was, you know, like that? So if it was something like that, it'll have almost the same, you know, Z magnetization, but it's going to have some transverse magnetization, XY magnetization, and that's going to create another signal over here. So there'll be, you know, that would potentially, you know, create down here another signal, and then that could sort of, you know, interact with this echo. You get a secondary echo. You know, you can see it's starting to get a little bit of a mess. And so then we use a crusher. And so a crusher is, if the 180 was correct, there shouldn't have been any transverse magnetization, because remember, the RF out, the only RF out that we can measure is magnetization transverse. So that's the only signal we can measure. So the crusher, the idea of the crusher is, it's just to wrap up some spin phase stripes of any spurious magnetization transverse that appears. So it's just to clean up the mess, because this might not have been exactly 180. But then what do you need this ear, this pre-crusher ear? And so the problem is, say there was some transverse magnetization before we started. Like, for instance, say we scrunched this in, and so, you know, the echo was starting to form, but it hadn't gone down to 0. And so there was some transverse magnetization that was already there. So in that case, we're going to mess it up, but we don't want to mess it up. We just want to mess up the transverse magnetization that came from the incorrect 180. And so if we do another lobe before there, you know, you might wonder, why is it up? Well, it's up because there's a 180 in between it. And so this thing is, if this thing is going to mess up some transverse magnetization that we want, then what this one is going to do is pre-unmess it up. And then when we do this one, the effect of this one on the magnetization that we wanted to keep, that came from before, will be canceled, and so we'll keep it. So it's so you can sort of, because the 180 is in between, what we're actually doing is we're essentially doing something like that, sort of pre-messing up the pre-existing transverse magnetization, and then afterwards crushing the part we don't want, but that came from the 180, but leaving, sort of fixing up the part that we wanted to keep, the transverse magnetization that we wanted to keep before the 180. So you always have that kind of thing going on as a way of cleaning up the signal from the 180 that wasn't like a perfectly good 180. Okay, so fine details, but it's always done. So, but before we do the 180, that we just do one of these pulses down here on the readout. So, just do one of these. So, one only. And so, what are the, let's put, so this is slice select, and this guy is phasing code. This guy is readout. Okay, so what does that guy do? So that gradient, it's in the x direction, is going to change our position in k-space. It's a positive gradient, and so by the time we get to B, so here's B, it's going to basically move us out to, all the way out to the right side of k-space. So again, in terms of what's actually happening in the brain, what is that doing? That's just wrapping up vertical spin phase stripes, positive vertical spin phase stripes. It's like a lot of them, like 128 of them. So that means across the whole brain there'll be 128 little wraps of the phase of the spin. And so then we'll end up at point B. So here's point B. You haven't recorded any data yet. And then we do the next thing. Yeah, make sure it's a small letter, isn't it? Yeah, okay. So the next thing is we do the 180. And so I won't draw what happens during the crushers, but after the crushers are done, then we get to point C in k-space. And so what that is we go to the conjugate part of k-space. And the conjugate part of k-space is just basically taking whatever kx and ky we were at and making them negative. And so negative kx goes to the opposite side. Ky was 0 because we're just right in the middle still. So negative 0 is 0. And so now we end up at point C over here. Still haven't recorded any data. Then what we do is we need to do a phase encode step. So here's so in practice you might actually overlap the phase encode step with that crusher, but I'll just draw it for the sake of illustration, not overlapped. Okay, so here's our phase encode, and so we just do one of those. That means repeat this whole thing, but with each multiple times with different settings of this phase encode gradient. And so after we've done the phase encode gradient, then we're at point D. So let's say we did a positive one. So if we picked out a positive one, then what's going to happen is we're going to start wrapping up spin phase stripes in the horizontal direction. I mean, as you go across the stripes, you'll go in the ky direction. So that will basically move us up to here, say say that's the 30 stripes or something, 30 stripes in the horizontal stripes, so 30 stripes moving in the y direction. So that's where we are at D. And then we do our readout. And so here's our readout like that. So that will, and then we record our data. So finally we're recording. So now we're recording. So here's all our data points. Like that. So this is, record, RF, record. We don't have the recorder on the whole time. Okay, so then that puts us over at point E, right? So here's point E. So now what will happen is we will turn the readout gradient on, which will sort of like unwrap the X stripes until you reach the center of K space, at least the center for KX, and then rewrap them up to positive 128. And during this whole time, we'll collect all the data. And so we collected like 256 points across K space for a particular, forgot to put the, so I have C, so here's point D, and then here's point E. Now, now the problem is we've got to wait a long time because we want a T2 weighted scan. We don't want T1 weighted scan. And so how long do we have to wait? Well, quite a long time, because you remember, if we wanted a T2 weighted scan, we're going to want to essentially find, we start at more or less the same point, and then we've got two different fall-offs. And so we want to sort of wait enough time for our time of echo. So here's the TE. So we want the time of echo to be long enough so that there's some difference, and this might be, say, 50 milliseconds right here at that point. So we want to wait, a reasonable time, 30, 50 milliseconds. But if we want to get a T2 weighted scan, we don't want some T1 in there too. And so what happens there is that it's going to take a long time until we get back up to MZ0. So here's, MZ0. And so if we've got two different tissue types that have two different T1s, we're going to have to, wait until like 3 or 4 seconds, which is kind of an eternity if you're sitting in the scanner. And you've got to do that thousands of times. So, and why are we doing that? Well, we're trying to get rid of this contrast. So if we did it just after 1 second, then there would be a strong brightness difference due to T1, not to T2. And all we want is the brightness difference due to, so this is, what we're plotting here was the transverse magnetization, and what we're plotting here was the longitudinal magnetization. But as soon as we do an RF pulse, it's going to turn the longitudinal magnetization into transverse that we can record, and then it will make our signal T1 weighted, and we don't want that. So that means you've got to wait like 4 seconds until you do that slice again. So here's our, so this is the TR right here. So that's the TR, for example, 4 seconds, long time. And now you can see why it's slow SpinEcho, because this was only one line in one slice. Now, since we're doing a slice, what we could do is let this guy recover for 4 seconds, this slice recover for 4 seconds, then do a different slice. So select a different slice and then work on that one. But the problem is, even after we've done that, we've done all the slices, there's still a lot of extra time just lolling around, just waiting for the recovery to happen. And so that's why it takes 45 minutes just to get one image of the brain with relatively thick slices. Might be like, 4 millimeter thick slices. But radiologists still like to use these, and one reason they do is because, so these slices, there'll be a thick slice, like 5 millimeter thick slice like that, but it will have these small voxels in it that extend throughout the slice. And so why would you want to look at a slice like that? And the reason is because if you're a radiologist, you're looking for something in the brain, you don't want to get confused by all these little thingies, because everybody's brain has little thingies. You got like a little hole here, tiny little micro stroke that occurred when you fell off the skateboard and slammed into the ground. And those things are kind of irrelevant for, a tumor that's actually going to cause some problem in your brain is going to be it's a chunky thing. And so when you take a relatively thick slice, it kind of smears out all the other details. And so that's one reason why radiologists still like to look at these thick slices, even though we can make much thinner slices now. Because it just kind of like blurs out the unnecessary detail. And there's a big chunk here that I can see that survived, blurring those slices. So these, like I said, these scans are still used, but not too much anymore because they take so long, 45 minutes just for one scan. And so then what was the advance? Well, I should have left those guys up. Let's just do more echoes. So here's GZ. So how can we do more echoes? So the plan is we can do like an echo train. And so the echo train was, if we do 190 and then do a 180, and then after time t equals tau, we get an echo. And then if we wait another time tau, and then a second time tau, then we'll get another 180 in there, and then after another time tau, then we'll get another SpinEcho. And so let's put this one's going to go all the way to the edge. So do the first part of it is the same, but I needed to squish it a little bit because there's more parts now. So here's the signal coming out, and here's when we record. So just like before, we do our 90-degree pulse, and then we pick out a slice, and then we sort of fix the fact that the slice picker outer messed up the phase, and then here's the FID coming out, and then we just do one of these right here, go to the right side of K-space, and then we do a 180 here, and then that one we've got to do the little funny ears on the thing to sort of clean up our 180 because it wasn't quite 180. And that doesn't, if that was a good 180, doesn't cause any signal down here. And then, or if there was some, we got rid of it. And then that amount of time afterwards, there's an echo. So here's our first SpinEcho. And so pretty much we'd be in the same place. So here's, as we were last time, so there's A, and then we went to the right side of K-space, that's B, and then we did the 180, and that's C, that flipped us to the left side of K-space, and then we did the readout. So here's the readout. So this is slice and phase, readout, frequency encode direction, that's the readout. And so then we end up across k-space at point E. So this guy is point E here. So, but I forgot to put the phasing code in, so we got to put the phasing code in. So that would be like right here. So we just pick one phasing code. There. Say we picked this positive one there. So that would put us at point D. Point D over here, and then we do the readout and collect our data. So now we're actually sort of collecting the data down here. Okay, so that I just redrew what I had last time. But now what we want to do is do some more echoes from the same 90. And so the plan is, so that was, time tau, and that was another time tau when the echo occurred. And if we wait yet another time tau in order to, read out all the echo, and then do another 180 right here, so there's another 180, then we've got to do the ears business again to select that slice. And in theory, it shouldn't give us any signal if it was a good 180. But now you can see what the problem is. We're over here. We've got like a bunch of vertical stripes from having done this readout, and then we've got some horizontal stripes too. So the stripes are actually kind of tilted a little bit. But they're mostly vertical stripes because we turned on the X gradient for a long time. And so if we just do another phasing code and readout, we'll just end up somewhere off in space. And so like really high spatial frequencies, useless high spatial frequencies. And so what we need to do is we have to sort of take into consideration we've got some transverse magnetization. It's hidden, but hidden transverse magnetization is still there. And so for that reason, we've got to sort of do another pulse that will sort of like straighten us back up again. And so the first thing we do is go back to the y equals 0. And so what is that? That's basically another phase encode like pulse that sort of fixes things up as soon as we finish doing our readout. And so that one is going to, what we want to do is just do exactly the reverse of what we did last time. And so sometimes the way people write this out is they write, let's go through all these steps in this direction and then go through all the same steps in that direction depending on like whichever one you picked. And so so by the time we're done with that, then we end up at point F. And point F is pretty much the same as, it's just the same as point B. So now we're ready to do another 180. And so when we do another 180, what happens? Well, we go back to this side of K-space. And so now we're at point EFG. And so G is the same as C. I guess that F should overlap B. There we go. It's like we're overlapping. Okay, so point G is back there, and then we can repeat. And so what does repeat mean? Well, now we've got to do another phasing code, a different phasing code. And so let's say we do a negative phasing code. So we'll start we'll do a negative phasing code this time. And so what does the negative one do? It goes like, so we're right here. It goes down, same amount as we went up last time. So that would be point A, B, C, D, E, F, G, H. So now we're at point H. So there's point H. And then we do a readout to go across. And then, sorry, it's supposed to be a solid line. And record all our data points. And so now we've recorded a second line from the same 90. And so that will put us HI. So that put us at point I. So that would be this thing again. So here's this amount of time later. There's another echo happening down here. So it's a smaller echo because there's more T2 decay. Because here's our e to the minus t over t2. And so while that echo is occurring, we've turned on our gradient, and we're recording another little burst of data here. So by the time we're done, it gets to point I. And then after that, we've got to undo our phasing code again. So this time we do a positive one to fix the negative one that we just used. So here's a positive one, and that will, so we're over here, and that will put us back there again. And so that would be point HI, point J. So here's point J, which is the same as point B. Okay, so now we can sort of like et cetera. So et cetera, for 16 echoes. So that's good, because then we can collect 16 lines of k-space just from 190. Because these times aren't very, very long, like the echo time. So, here's the TE. The echo, that echo time is, 30 milliseconds, 50 milliseconds, something like that. That's a small amount of time compared to 4 seconds. So we can easily do 16 of these. But now, if you look at this, you can see why it's not quite as morally upstanding a pulse sequence as our other pulse sequences, because all the echoes have different T2 times. Because what's the second echo? The second echo, what's the TE of the second echo? Well, it's actually the second echo over here. So this is, TE of the first echo. But this is TE of the second echo. So it's not the same. TE2. And then, the 16th echo is going to have a very long TE. So that's a little worrisome. So it means that different lines of k-space have different amounts of T2 weighting. And that's actually the case. So how do you use this sequence? Well, you could, if you want a T2 weighted scan, then you want kind of a longish echo, because you're looking for, I drew it before, but I'll draw it up again. So, if you're wanting a T2 weighted scan, here's like one tissue type and here's another tissue type, like that. So you're wanting kind of a longish echo time, which might be, say, like, 40 milliseconds, where there's a big difference. But why waste 40 milliseconds when we could just do this first echo very quickly. We could do this one in like 5 milliseconds or something like that, or 10 milliseconds, very short. And so we'd be wasting all this good signal here. And so what you can do is you can essentially decide to collect the center of k-space with either a long echo time or a short echo time. So basically the center of k-space, TE, is called the TE effective. So that's the one that will, there's a homework problem on it. That's the one that will most strongly affect the way the image contrast looks, is the center of k-space. The very center of k-space affects it, but some of the low spatial frequencies affect it too strongly. And so what we can do is, if we want to make a T2 weighted scan, what we do is, if we look at our echoes we will basically wait to collect the center of k-space. So collect other parts of k-space first. Now the signal from other parts of k-space are smaller, and so if we just look at our magnetization transverse, what it looks like is, here's that first echo. It's in a high part of k-space. It's got a big starting point, but we've wrapped up a lot of spin stripes, and so that really lowered the echo amplitude. And then if we're doing 16 echoes, as we get closer to the center of k-space, the whole thing's dying off, but as we go closer to the center of k-space, that makes our biggest echo. And then we can collect, some more of them like that. So basically what will happen is, so this is, collect center late. So, big TE, that means T2 weighted. So just by collecting the center of k-space late, we get a T2 weighted scan. But alternatively, what we could do is we could collect the center of k-space at the very beginning, in which case we get a really big echo. And then we would get a proton density weighted one, and then collect other parts of k-space later. So this, if we collect the center, k-space center late, we get a T2 weighted. If we collect the center of k-space, so now we here collect, center k-space. Center k-space early, then there hasn't been much time for contrast, and so we get a proton density weighted. So this guy, PD. So, and we could even do both of these at the same time, which is commonly done. So this is proton density weighted, because sometimes we want to actually just look at proton density. So this is a very common sequence, and you begin to see some of the trade-offs that occur, because you've got all these different echo times. So different parts of different spatial frequencies have different T1 and T2 weighting. It's kind of weird. A lot of times if you do this kind of symmetrically, or you can sort of cancel out some of these inhomogeneities between the different echo times, and but this gives you some ideas as we slowly push it faster and faster. And then when we talk about 3D fast spin echo or the space scan, we can see we're really ramming things at super speed and doing even more shortcuts than before. But the end result, even though the image isn't quite T2 weighted, we were able to collect the data so quickly and with such high resolution that sort of wins. And that's why we use these more sort of optimized sequences. But they're not just optimized, they're slightly tweaked in a way that makes them sort of a little bit more difficult to interpret than the old slow spin echo. And so that's that's some of the use for slow spin echo. If you've got a new sequence and you want to see, like, how well is my new sequence doing, we can go back to slow spin echo to see what the true answer is, and then see how close you've gotten to the true answer. Okay, so that was FSE, turbo spin echo. So it's a very common pulse sequence that you would use for a clinical scan or for an anatomical scan. We would do these often. Do one of these space scans and take another scan and divide it by the space scan to normalize things. Okay, so went over slightly. Any questions about where we are? So I mean, like so the diagram here, this k-space diagram here is basically our simple 2D way of thinking of this much more complicated reality, which is stripe patterns. So do the 90, get to the center of k-space, come out in 3D, go back when we select our slice, and then we only got to do this guy once. This guy is once only. Go to the right side of k-space only one time, and then do a 180. Go somewhere in yk space, read out some data, fix up where we were in yk space, do another 180, puts us over here, go to some other place in k space, different stripes, and then unwind and then rewind the vertical stripes, collect a bunch of data, and then fix that, so you can just sort of keep going like 16 times. So that was fast spin echo. Okay. Any questions out there? I kind of bowled my way through with not any space for questions. Okay. Little question? Any question? All good? Sort of. Yeah. Okay, so pulse sequences. So we'll just, over the next week or so, we'll go over all these different practical modern pulse sequences.